If you're given a system of linear equations and you want to solve it, such as 2x plus y equals 1, x minus y equals 7, the way you probably do that is to manipulate those equations, for example by subtracting a multiple of one of them from another, or multiplying one of the equations by a constant, until you can read off the solutions. We now know how to put these equations into a matrix form, and so we're going to be interested in this video in what's the effect of these manipulations from a matrix point of view. Here's a specific example of solving a linear system. So consider the linear system which I've written here. 3x plus 4y is 6 and x plus 2y is equal to 5. One possible way to solve them would be to begin by eliminating x from equation 1. So what that means is subtract 3 times the second equation from the first equation. When you do that, you don't change the second equation, but the first equation becomes minus 2y is minus 9. One possible next step is to make the coefficient of y in the first equation equal to 1 by multiplying by minus a half. Then the first equation will become y is equal to 9 over 2, and the second equation wouldn't change. Then finally what you could do is eliminate the x from the second equation by subtracting 2 times the first equation from the second. And if you do that, the first equation doesn't change and the second equation becomes x equals minus 4. You've now manipulated these equations to a point where you can read off the solutions. We know how to express these equations into in a matrix form, so in the form A times some vector of variables is some vector of constants. We're going to look at the effect on manipulating equations in the ways which we've just done on the matrix form of these equations, and specifically on the augmented matrix associated to the matrix form of that equation. And it turns out that the effects can be described by what are called row operations. Here's the definition of a row operation. A row operation is one of the following 3 different things which you can do to a matrix. First, adding lambda times row I to row j. And in this case, lambda is a number and j is a row not equal to I. The second type of row operation is multiplying row I by lambda, where lambda is not equal to 0. And the third type is swapping 2 rows I and j. You'll see on this slide that each row operation has a specific notation. The first type of row operation is written like this, so row j goes to row j plus lambda times ri. The second row operation is written like this, so row I goes to lambda times row I. And the third row operation is written as ri swaps with rj like this. Let's briefly look at some examples of row operations then. So we will take A to be the matrix 1, 2, 3, 4. If we were to do the following row operation, where R1 goes to R1 minus R2, then what we will get is, well, I subtract row 2 from row 1, so I get minus 2 in the top left, that's 1 minus 3, and I get minus 2 again in the top right, that's 2 minus 4, and I don't change the second row. On the other hand, if we take the same matrix and we do the row operation which multiplies row 1 by minus 1, so that's written as R1 goes to minus R1, then row 1 will become minus 1 minus 2 and row 2 wouldn't change. And as the final example, if we were to do the swap rows 1 and 2 row operation, then what we would end up with is 3, 4, 1, 2. Those are the 3 different types of row operations, and they correspond to manipulations that we commonly do to systems of linear equations. You'll see how shortly. The last thing I'm going to say about row operations is that they have an extremely important property, which is that row operations are invertible. What I mean by that is that for each row operation R, there is another row operation S, such that doing S then doing R, and doing R then doing S are both the same as doing absolutely nothing to your matrix. For example, the row operation which sends row j to row j plus lambda times Ri has inverse the row operation which sends Rj to Rj minus lambda times Ri. If you think about the meaning of those row operations, you can convince yourself very easily that doing them in either order is the same as doing nothing to your matrix. Next, if you consider the row operation which multiplies row I by the non-zero constant lambda, then that has as inverse the row operation which multiplies Ri by 1 over lambda. Again, I think it's very clear that if you do those two row operations in either order, that's the same as doing nothing. You simply end up multiplying row I by lambda times 1 over lambda, which is just 1. Finally, the inverse of the row operation which swaps row I and row j is the row operation which swaps row I and row j. That row operation is its own inverse, because if you swap row I and row j twice, then clearly you're back to where you started.